Hello! In this video, we will consider finding the volumes of solids using cylindrical shells, this time contrasting the use of cylindrical shells with washers. Suppose we have the region bounded by the graphs of y equals 3 times e to the negative x, the x-axis, and the lines x equals negative 1/2 and x equals 2. This region is rotated about the line y equals 6. We want to find the volume of the resulting solid. So as we have before, let's make sure we sketch the region in the three-dimensional solid. So here's a graph of the region, and if we sketch the solid that results, this segment between x equals negative 1/2 and x equals 2 is 6 units below the axis of revolution. So when we revolve it about the axis, we're going to be placed up here at y equals 12. So I'm going to get this right here. This tip right here of the region is just a little bit more than 1 unit away from the axis of revolution. So it's going to be just a little bit above 1 unit away from the axis of revolution here. This piece right here at x equals 2 and 3 times e to the negative 2 will come up here and get this little ridge here. And we can complete the rest of the curve. It's going to look basically like a bowl, but there's a hole in it, which will not make it very useful. Another perspective of the three-dimensional solid is given here based on Mathematica. And so we want to consider what happens if we try to find the volume of this solid using the shell method. As in every problem, we want to watch to see if calculus is truly needed to solve the problem. And in this case, it's actually not needed to determine the volume of part of this solid. If I, in line with using the shell method, draw rectangles that are parallel to the axis of revolution, I notice that this region right here, given by this rectangle, is different than the others, in that the right edge of this rectangle is entirely along the line x equals 2, whereas all the other rectangles have just a corner of the rectangle touching the function, so that makes it different than the other rectangles. So when I consider this bottommost rectangle and the fact that its right edge was entirely along the line x equal 2, I don't need calculus to find the volume of the portion of the solid determined by rotating that rectangle around the axis of revolution. I do, however, need calculus to determine the volume of the rest of the solid. All of these other rectangles have their left edge along the line x equals negative 1/2. The upper right corner of the rectangle is based on the curve y equals 3 times e to the negative x, and that is used to produce the rest of the right edge of the rectangle. And these particular rectangles sit between 3 e to the negative 2, which is right here, less than or equal to y, less than or equal to 3 times e to the positive 1/2, which is what we get when we plug in negative 1/2 into the function. So therefore, because of these two different parts of the region, we need two different calculations in order to get the volume of the solid if we want to pursue the shell method. So this first part, we actually don't need the shell method. We're not going to use calculus, but we'll consider the portion of the solid that results from rotating the rectangle adjacent to the x-axis about the line y equals 6. And as I said, we don't need calculus to determine this portion of the solid, the volume of this portion of the solid. If the rectangle has as its bound the x-axis, x equals 2, y equals 3 times e to the negative 2, which we get by plugging in positive 2 into the function y equals 3 times e to the negative x, and x equals negative 1/2, we can identify the dimensions of the resulting solid and find its volume. Now, if you notice in this solid, it's actually two concentric cylinders, and so therefore we can find the volume by finding the difference in the volumes of the cylinders. Recall that the volume of a cylinder is the area of the base, pi r squared, times the height. So if I want to find the difference in those volumes, I need to find the radii. So the radius of the outer cylinder is going to be determined by this axis of revolution at y equals 6 down to the y-axis at y equals 0. Okay. The inner radius will come by determining the difference in the y equals 6 and the value of my function there at x equals 2. So the inner radius comes from 6 minus 3 times e to the negative 2. So the volume of the portion of the solid that's from that outer edge is determined by pi times the square of the outer radius minus the square of the inner radius times the height. And the height is determined by the difference in these x values. So x equals 2 minus x equals negative 1/2. So I'm going to plug those radii and the height in. So I've got pi times 6 squared minus 6 minus 3 times e to the negative 2, quantity squared times 5/2. I'm going to expand and simplify, so I get the volume of this outer portion of the solid as being pi times 36 times e to the negative 2 minus 9 times e to the negative 4th times 5/2 to give me approximately 36.97 cubic units. Again, I did not need any calculus for this volume. For the second calculation, we partition the interval y between 3 times e to the negative 2 and 3 times e to the 1/2 and consider revolving the kth rectangle of the partitioned interval around y equals 6. We want to identify the dimensions of the resulting solid and find its volume. So the kth rectangle is here in orange, and I want to revolve that around the axis of revolution, which is at y equals 6, and I get a shell that looks like this. Okay. Now the radius of the shell comes from the axis of revolution down to y sub k. So I can simply calculate the greater minus the lesser, or the top minus the bottom, so that's 6 minus y sub k. The height of this shell is based on the x value when I've got y sub k minus x equals negative 1/2. If I've partitioned the interval y going from 3e to the negative 2 to y equals 3 to the 1/2, because my rectangles are parallel to y equals 6, I need to solve my equation for x so I can find that difference in those x values. So y equals 3 times e to the negative x sub k means that x sub k is equal to the negative natural log of y sub k over 3. So that gives me the height of that cylindrical shell as being x sub k minus a negative 1/2, or in other words, negative natural log of y sub k over 3 plus 1/2. So therefore, when I put these pieces together, I can get the volume of the cylindrical shell. So that's 2 pi times r sub k times h sub k times the thickness. So I've got 2 pi times 6 minus y sub k times the natural log of y sub k over 3 plus 1/2, all times delta y sub k. And delta y sub k is the thickness of that shell determined by the difference in the width of that rectangle. To get the volume of the interior portion of the solid, I can simply sum the cylindrical shells. So I've got k going from 1 to n of 2 pi times 6 minus y sub k times the quantity natural log of y sub k over 3 plus 1/2 times delta y sub k. As I take the limit of that sum, as the norm of the partition goes to 0, in other words, as the width of the rectangles go to 0, I get the definite integral of 2 pi times 6 minus y times the natural log of y over 3 plus 1/2 dy. And because I partitioned the interval from y going from 3 times e to the negative 2 to y equal 3 to e to the 1/2, those become my limits of integration. Again, this is an integral that I am not able to solve unless I have integration by parts, which is something we'll discuss next chapter, so I can use technology to approximate the value of this integral to be 96.02. So when I put those two pieces together, I find that the volume of the entire solid is approximately 132.99 cubic units. Now, let's find the volume of the same solid using washers, or in other words, using volumes by cross sections. I've got the same solid that results, but this time I'm going to take slices that are perpendicular to the axis of revolution. So therefore, we will partition the region using thin rectangles on the interval x between -1/2 and 2. So when we partition that region, we notice that each rectangle has boundaries that are determined the same way. The top edge of the rectangle is determined by the function y equals 3 times e to the negative x, and we're going to rotate the kth rectangle about the axis of revolution, and we want to draw the washer that results and find its volume. So the outer edge of the washer will go from here. Then I've got the thickness here is our x sub k minus x sub k minus 1, and then the inner portion of the washer will come from the function value at x sub k. Using some technology and drawing a washer, it looks like this. And the volume of that washer will come from pi times the difference of the square of our inner and outer radius times delta x sub k, which is the thickness of our rectangle. So that outer radius comes from, again, the greater minus the lesser. In this case, the outer radius comes from the axis of revolution down to the x-axis, so the outer radius is 6 minus 0. The inner radius is that from the axis of revolution down to the function. So it's going to be 6 minus 3 times e to the negative x sub k, quantity squared. So expanding and simplifying, I get the volume of the kth washer is pi times 36 times e to the negative x sub k minus 9 times e to the negative 2 times x sub k, all multiplied times delta x sub k. I'm going to carry this over to the next slide to get when I sum the volumes of the washers, and I'm going to get the Riemann sum, k going from 1 to n, of pi times 36 times e to the negative x sub k minus 9 times e to the negative 2 times x sub k, all times delta x sub k. As I take the limit of the sum, as the norm of the partition goes to 0, or as the width of the rectangles goes to 0, I get pi times the definite integral from -1/2 to 2 times 36 e to the negative x minus 9 times e to the negative 2x dx. And recall that because I partitioned the interval from x equals -1/2 to x equal 2, those limits of integration come from the interval that I partitioned. This is an integral that for which I can find an antiderivative. So I have pi times negative 36 e to the negative x plus 9/2 e to the negative 2x. I'm evaluating this from -1/2 to 2 to give me approximately 132.99. In my opinion, this method was much easier than trying to use shells to compute the volume, and I didn't have to do two separate calculations. I didn't have to solve for x in terms of y. It was relatively straightforward. So here are some important ideas to take from this video. In many cases, we can find the volume of a solid by revolution using both washers or cylindrical shells. Now, if cylindrical shells are used to find the volume, the thin rectangles used to partition the two-dimensional region must be parallel to the axis of revolution. If washers are used, then the thin rectangles used to partition the region must be perpendicular to the axis of revolution. And depending on which interval you're partitioning, determines whether you integrate with respect to x or with respect to y. Depending on the region and the equations used, one method is often easier to use than the other. The more challenging method, shells or washers, may require two separate integrals or two separate calculations to determine the volume. This was the case with using the cylindrical shells in this video. The two calculations were required because the two-dimensional region partitioned into rectangles parallel to the axis of revolution had different sets of boundaries. Also, in this example, the use of cylindrical shells required that we solve for x as a function of y. When calculating volumes, please be careful. It's often possible to solve parts of these problems without using calculus. Make sure you don't make more work for yourself than you need to. And finally, when using either cylindrical shells or washers, it's essential that you draw multiple diagrams. Make sure you label the dimensions of the shells or the washers, determine the volume of the kth shell or washer, and then set up the Riemann sum and take the limit as the norm of the partition goes to 0, which produces the definite integral. Have fun calculating volumes.